Welcome, everyone. Thank you for joining our fourth webinar in our simulation series and the last webinar before 2024. My name is Patrick Kenny. I am the Senior Director of Marketing and Communications for Invest Ottawa and Area X.O, operated by Invest Ottawa. For those of you that are not aware, Area X.O is an Ottawa-based research and development facility featuring a 1,866-acre private testing facility, unique smart city infrastructure, physical and simulated assets, and one of the most advanced communications infrastructures in the world. All this allows our clients and partners to test and validate exciting new technologies across all sectors. This past year, Area X.O launched a new simulation discovery portal powered by Ansys. The simulation portal and program promotes simulation and its ability to reduce time, cost, effort, and risk to get breakthrough technologies and innovations to market faster. The program is also offering limited time free project opportunities until the end of March 2024. To start things off, let's view this introductory video on Area X.O's simulation capabilities.
So, you're a smart mobility innovator looking to stay ahead of the curve? Look no further than Area X.O's new simulation discovery portal powered by Ansys. This free portal promotes simulation to reduce time, cost, effort, and risk to get your innovations to market faster. With one of the most advanced communication infrastructures in the world, Area X.O offers limitless testing capabilities for smart intersection and autonomous vehicle technology. But safety is critical. That's why the free portal showcases a digital twin of the physical Area X.O facility that could be used by qualified companies to test and refine their innovations before moving to physical infrastructure testing and further product investment. Free access to the Area X.O simulation discovery portal community includes opportunities to learn about the benefits of simulation, access MathWorks and Ansys curated content, as well as the ability to interact with sample Area X.O assets in a virtual environment. Full premium access is available for qualified participants and provides access to Area X.O simulation engineers and the opportunity to build customized simulation solutions. Don't miss out on this opportunity to be part of the smart mobility revolution and to learn more about simulation as a solution. Register now.
We are excited to launch today's seminar focused on unleashing the power of 3D mapping and simulation in autonomous vehicle software development. This webinar is coming to life today through a unique simulation success story with Area X.O client 4DRobotics. Representing 4DRobotics today will be Alyssa Turner, who oversees autonomous vehicle research and development for 4D. She will be joined today by Area X.O simulation engineer Hossein Sami. Before we begin, here are a few housekeeping items. For any chat opportunities or questions you might have, please enter them directly into the YouTube chat. We will have a specific Q&A period following the end of both presentations. To test out the chat, we would love for you now to test it out and answer the following question. What sector of focus do you represent? Please add that to the chat. Feel free to also jot down this email address, simulation@areaxo.com. That's simulation@areaxo.com. Any questions that aren't answered today, please send those to that email address and we'll get back to you shortly. We will now turn things over to Alyssa Turner. Alyssa oversees autonomous vehicle R&D for 4DRobotics, and we're excited to see her presentation today. Alyssa, over to you. Alyssa, just come on.
All right, can you hear me?
I can. We're excited to hear what you have to say today, Alyssa.
All right, perfect. So, as he just said, my name's Alyssa. I work at 4DRobotics Corp. I'll be talking to you today about how 4DRobotics uses simulation in the development of our autonomous service vehicles and how we worked with Area X.O and Ansys to improve on this. So first, a bit about 4D Robotics. So we are developing and marketing the autonomous vehicles as a service solution that is used to automate routine hazardous tasks normally performed manually outside in all weather conditions. 4D Robotics products employ artificial intelligence and sensor fusion to understand the real world and to reason with this information in real time. This is used to guide autonomous uncrewed vehicles that remove humans from hazardous tasks and are deployed for essential applications to reduce operating costs by completing tasks reliably and consistently in less time. All of our vehicles and team management solutions are developed and manufactured in Canada, with the majority of the R&D team working here in Ottawa in Bells Corners. I joined 4D Robotics as a co-op student in 2020, worked there throughout my engineering degree, and joined on as full-time in May of this year. Since 2021, I've focused mostly on creating and developing the simulation we use to test our vehicles and our software. So the problem. Testing an outdoor uncrewed autonomous vehicle is not a trivial task. It must be done carefully, as it can be quite dangerous in the early stages of development, where there can be many problems, and is a time-consuming and expensive process using physical vehicles and resources like Area X.O. The best solution to this is to test with simulation before testing in the field. Simulation allows us to complete more testing because we do not need to reserve space or expend the logistics need to conduct outdoor tests. It's also much safer, as it can't cause harm to people or property, and exhaustive testing can be done on any vehicle, even if it's not physically built yet. This will be very useful for integration and testing of new vehicles and can accelerate the R&D process for making more vehicles autonomous. One of the necessities for having a functional simulation is to have a simulation environment that matches a real environment. This way, tests conducted in the simulation can be repeated in real life, and the validity of the simulation can be verified. A lot of the simulation environments used today contain only a flat ground with objects in them like buildings, streets, signs, and cars. These can be automatically generated from OpenStreetMap's data fairly easily. This works fine for many drone applications that don't need to traverse over uneven terrain, or even for cars that just care about staying in the lines and things like that. But an autonomous ground vehicle's movement will be affected by uneven terrain, especially if going off-road, so terrain variation needs to be included in the simulation environment. When I started working on the simulation at 4D Robotics, I spent a lot of time finding resources to create an accurate 3D model of a small portion of Area X.O called the school zone, which you can see in the center picture there, but there's not much available. Unlike the USA, which has an abundance of fairly easily accessible LiDAR maps of most of the country, or at least the main populated parts, I was only able to find height map data of the terrain in Ottawa from satellites. So this is pretty accurate. However, it's not centimeter accuracy, and anything that is blocking the ground is going to give a different height, pretty much. So turning this height map into a 3D model and overlaying high-resolution satellite imagery on it, combined with manually adding buildings and signs to the model, created a map that worked well enough for testing the autonomous motion of the vehicle, but the sensor data wasn't very accurate since most of the visuals were very pixelated, as you can see in the pictures on the left and the right here. So these are our old map of just the school zone that had the overlaid image and just some basic terrain and basic buildings, railroad crossing, things like that. So it also took a lot of time and measurements to manually add objects in the correct positions in this map. So it worked for initial testing, but it's a good thing that Area X.O solved this issue for us. So Area X.O, like I said, solved this issue. They developed a high-resolution 3D model of their entire testing facility called the Digital Twin that you saw in the video previously as well. This was created with massive LiDAR point clouds and accurate measurement verification. This map has been imported into the Ansys simulation tool, where material properties were applied to all objects in the model to ensure accurate sensor data simulation. And then it was also imported into WeBots, which is our simulation software, or the one that we use, for accurate physics calculations with the bounding terrain. This map has been very beneficial to us for accurately testing lateral and longitudinal controllers for the 4D Robotics autonomous service vehicle, as well as for object recognition and classification using simulated camera data. So in the pictures on the screen, you can see just some side-by-sides of the simulated map and the real, just real footage from Area X.O. So the map is very accurate and very high detail. It works very well for all of our applications so far. So I'm going to show a video that shows our simulated autonomous service vehicle driving through the digital twin of Area X.O in Weebots, which again is the simulation software that we originally solely used and now still somewhat use. So this is mainly just to show both our vehicle, the simulation physics, and just mainly the high quality map and what it's capable of. So there's no sound, but it's just kind of showing first some real life versus simulation videos just to show the accuracy of the map. So I'm hoping the video is streaming fine and not laggy. But yeah, so you can see in the background all the buildings and everything that are at Area X.O. You can see lots of signs that are high accuracy, high detail. This is showing the articulated camera that we have on our vehicle that we can control in Weebots, and the articulated hatch that we have as well, and just various lights and things. So you can see the stoplights there the stoplights that the vehicle's going through. It also has working turn signals and stuff, which you'll see in a moment. But this is mainly just to show the high detail of this map that is really great. So as you can see, the ground is not flat, which is really important for our vehicle because it's supposed to be an off-road vehicle. It's ideally supposed to be able to traverse any terrain. So this can help with just when we're running our longitudinal and lateral controllers to move the vehicle and keep it on a path. The uneven terrain will often push it off the path slightly instead of just following the path exactly. And then we can adjust our software to adapt to that and have the vehicle correct for itself, which is pretty important. So that's why we needed the terrain differences instead of just a flat map like from OpenStreetMaps and things like that. And the suspension is fairly accurate. There's a couple bugs for me to work out. You'll see the wheels a bit weird sometimes, but other than that, it's so far we use it to test our autonomous software pretty well. As you can see there as well, that was put in on purpose to show that the signs and objects are things that the vehicle can hit, but the bushes are not. So it can go through bushes, but the signs, buildings, ground, some trees as well, like bigger trees, are all 3D objects that the vehicle has to avoid, which means that it'll also be able to pick it up in LiDAR and things like that. So this part of the video is showing some sped up footage, mainly just to, again, show more of the map and just the detail in the roads, the detail in the signs, just a bit more zoomed in here. And we're just, my coworker and I were trying to find where the more interesting looking places in the map are and show them off, kind of to give an idea of how great this map is and how useful it is, both for testing and marketing and just all of these things. So the building that the vehicle is about to go past is the building that you saw in the video previously. That's the main building, main office building at Area X.O. So it's got especially high detail around that, I find. And anyone who's actually been to Area X.O will recognize this as well, and see how crazy this map is, how accurate it is, especially compared to what we had before. So the 4D robotics simulation enables testing the same software that controls our physical autonomous service vehicle, known as the ASV, before doing any field testing. This includes our middleware using the data distribution service DDS, our human machine interface, our sensor fusion, and our autonomous or teleop missions. We test our software mostly with WeBots, which supports the Open Dynamics engine, commonly known as ODE. Given a vehicle CAD and a map with high-resolution 3D information, like the one that I just showed you from Area X.O, with details such as buildings, signs, and roads, the physical and optical testing is realistic. The main disadvantage of WeBots, unfortunately, is that the surroundings don't have certain material properties that can affect sensor data from LiDARs, radars, and thermal cameras. Things like metallic properties, temperature, things like that. So this is where the use of Ansys becomes very beneficial to us, since, as mentioned before, the entire simulated environment includes advanced material properties that affect how the sensors perceive data. So these properties include temperature, radiation emissions, and metallic and dielectric properties. Each sensor is also defined using dozens of physical and electrical parameters, such as a LiDAR scanning sequence and pulse energy, which I'm sure Sammy might talk about, or a camera's aperture, image sensor, and lens characteristics. Each sensor can also be calibrated to have the same biases, noise, artifacts, and physics limitations of any real sensor. So you can model really any off-the-shelf sensor specific to that sensor instead of just a generic sensor that is of that type. This can make the simulated sensor data so similar to the real-life test data that it can be used in the same sensor fusion algorithms without changing any configuration. So the data that's recorded from Ansys can be passed off to the people doing the sensor fusion tests in our office, and they can use that in the exact same programs that they use the actual test data. So the Ansys simulation focuses on the sensor data acquisition part of the simulation, while the WeBots simulation focuses on calculating the physics and the movement of the vehicle. So it works using a co-simulation bridge, which is used to send data about the vehicle's movement from WeBots to Ansys. And Ansys takes this data and moves the vehicle with all of the sensors mounted on it through its environment at the same time as it moves through the WeBots environment. Simulated cameras, LiDARs, and radars, including a thermal camera, then collect data in the Ansys environment, which can be recorded and used in the same sensor fusion algorithms developed by 4D Robotics. Data sent from WeBots to Ansys includes both position and orientation, so the sensors in Ansys see exactly what they would in WeBots or in real life going over that same terrain. So now I have a second shorter video that's just showcasing WeBots and Ansys running together using the co-simulation bridge. So the left screen is WeBots with its internal cameras, and the right screen is just a camera that has been mounted up and behind the Ansys vehicle. So just to give a view that's similar to the WeBots view and to show more than just what a sensor on the front of the vehicle would see, for instance. To show that the vehicle is actually there and can see itself. So it's only streaming, when I made these recordings, it was only streaming this one camera, just to speed up simulation, because simulation takes time. I think this video is sped up 2 or 3 times for just to make it look, or make it not just be super slow when I'm showing it, but it's for simulation and running, like collecting data and stuff, the real time doesn't really matter as much. This is again showing the backside of the main building at Area X.O. You can see the differences in Ansys and Weebots. Mainly that Ansys has a lot more information, especially about the sunlight, current and the reflections off of the ground and things like that. I think I have the sun a little bit too strong right now, but it's adjustable, and it will be fine-tuned. As well, the window is very small right now, again, just to speed it up to show the rendering and everything. You can adjust the resolution, you can adjust pretty much everything you want to, and then save all that data for yourself instead of just rendering it and getting rid of it. You can also see in the Ansys simulation, the street lights have actual lights in them. So that one was green there. So those can be actuated, from what I understand, during the simulation. So you can also see that the vehicle, as it bounces around and moves side to side and things like that, I'll just rewind it a bit to show that again, if it lets me. As the vehicle moves side to side, the Ansys vehicle also does the same. So if the vehicle flipped, for instance, which hopefully it doesn't, but again, it's simulation, we can always hit restart, then it would also flip in Ansys and all of the orientations and everything would be correct still. So, while the simulation currently is only recording data for future use with our fusion algorithms, eventually we do plan to stream sensor data from the Ansys simulation the same way that it's streamed to our vehicle control software from the actual vehicle, so that the simulated vehicle reacts to the data as it's received. This is crucial for the vehicle to understand and make decisions based on its surroundings during autonomous missions. We plan to expand upon the current environment as well, hopefully, to add dynamic objects such as railway crossing arms or easily actuated stoplights that will change fairly often, or with user commands, and additional weather conditions like the winter environment that Sammy has worked on in the Ansys software. So further, we want to simulate a team of collaborating autonomous vehicles, as shown in the diagrams below, that will work together to complete missions. This simulation is also a very useful tool for integration and testing of new vehicles before they're manufactured, which can accelerate the R&D process for making other vehicles autonomous. This is very beneficial to us, especially with clients who want certain changes to the vehicle, since our software is not vehicle specific. It can go on any vehicle with just some configuration parameters changing. So having the ability to import a CAD and just run the simulation with a couple tweaks is very beneficial. Lastly, the simulation can also be a very helpful tool for both training and sales purposes, since it looks and behaves near exactly like real life. So that's about it from me. Again, my name's Alyssa. I work for 4D Robotics. Feel free to ask me any questions during the question period at the end of the show after Sammy goes. You can also contact me at the email shown on the screen. Yeah, with that, I think I'll pass it off to Sammy.
Thanks so much, Alyssa, for pulling that together. So I have walked on those streets, I've touched those trees. I still find it jarring to see the level of detail and how it's then represented within the digital twin. It's remarkable, and you certainly touched on that. I'll remind everybody that this pop-up is reminding us all that if you have any questions for Alyssa, don't lose those, put them into the chat now or jot them down so that you can add them after, because she will be available and be able to talk specifically about her use case. I also wanted to let everyone know that this entire case study has been written up as a success story and featured on the Area X.O website. We have many success stories there that are all sector-based, take a look, work through those whenever you get a chance, and see some of the other great examples of companies working with us hand in hand on their technology. It's now my pleasure to bring up Hossein Sami, who is a Area X.O simulation engineer. Hey, Sami, good to see you. We're excited to see the Area X.O perspective in your presentation.
Yeah, for sure. How's it going, everyone? Nice to meet you. I'm Sami, one of the simulation engineers, and part of the team that's here at Area X.O to help small, medium companies in Canada develop their products. So I'm going to start off by giving a quick overview of the different simulation tools that we have at Area X.O through Ansys to support our clients with. So there's 4 main software packages we're using. What Alyssa showed you was using our AVaaS product. That's for developing sensors allow you to simulate autonomous vehicles. We also have SDK, which supports drone operation as well as satellite operations. And we also have HFSS, which is for simulating electronics, and SPIOS, which helps us simulating cameras. I'm going to be going into more detail for each of these, but yeah, so just hold on tight, just kind of let you know what's coming. So the first software I want to talk about, of course, is Ansys AVaaS. So Ansys AVaaS lets you simulate a few different sensors. We're allowed to simulate optical and thermal cameras. We're allowed to simulate rotating and flashing LiDARs, as well as radar systems. These are by far the most common sensors that are implemented on autonomous vehicles right now. We're able to design the sensors to the specific level of what lens go into the camera. Being able to control this much like fidelity into the physical parameters of the system allows you to really fine-tune its performance. This allows you to change the focus of the camera and modify parameters and choose what type of product would be suitable for your application before you need to purchase anything. Multiple sensors can be implemented on the same vehicle and allow you to integrate sensor fusion algorithms, as Alyssa was talking about. One of the things I also want to mention is the sensors that are modeled also account for the sensor noise as well as air generation to give you a realistic render. This makes it not just a computer simulation assuming ideal content, but it adds that randomness that we encounter in reality. What I also want to mention here is, yes, the Ansys environment, unlike a lot of other digital twin simulation software, includes more detail. Each of the materials, including the road, the trees, the leaves, and everything from the buildings to the ground, includes not only the optical properties of the surface, but also its dielectric properties. This tells you how the material responds in the electromagnetic spectrum and gives you more accurate responses from flashing LiDARs as well as radar systems, which depend on these frequencies. One of the things that we want to mention as well is AV Accelerate is very adaptable and able to integrate with simulation tools that existing companies have. So for any companies that are already using simulation tools, such as Carla, Weebots, CarMaker, whatever it may be, AVX is able to integrate with what you already have to add another layer of complexity and data to help improve your simulations. We also want to elaborate, like Alyssa was mentioning, that she wishes there's work to make the sensor simulations applicable to the hardware that's being set up. We've also done work with our Area X.O assets to apply this. And right now, when we run the AVX simulation through Ansys, we're also able to stream data directly from our autonomous vehicle, the Lexus, on site. This allows you to real-time compare footage from what the sensor sees in the physical car to what the simulation sees. This allows you, in simulation, to put the car into scenarios that don't endanger it. For example, we could have the scenario of driving up to the rail crossing, which it's been going on a loop, so it'll come back, I'm sure. But we can actually actuate the arms and simulate that the sensor is seeing the arms shut down to ensure whether the autonomous vehicle is able to detect that and respond accordingly. Doing so in the physical test track is risky before you validate because you might end up damaging the car as well as the infrastructure. Yeah, so just wanted to elaborate, we have that. One of the other great things about Ansys AVX and what we are able to provide at Area X.O is our digital twins. We have HD models that have been generated for our physical site. This includes Area X.O as a whole, which is all of the roads, as well as the sensors that are mounted on the infrastructure. We have our rail crossing, as well as our four-way public intersection replicates that are on site, mimicked into the Ansys software. This allows you to simulate exactly the test case that you want to test physically at our site before you even come here. We're also able to run multiple iterations and determine exactly what is the most interesting case for you to physically simulate when you're here. Another thing that I want to mention is we also have a digital twin of our DART site. The DART has been released. It's focused more on drones and robotics. It's the Drone and Advanced Robotics Training Testing and Training Zone. Sorry, but this environment can also be used in conjunction with Weebots, as shown, to train operators to be able to fly drones and maneuver throughout these obstacles. It can train operators to be able to control their rovers and robot dogs, etc., you name it, through these obstacles, and ensure that the operator being trained is able and ready before they come to the site for actually training on the environment. Awesome. And all of these environments, I just want to reiterate, has the high level of detail. From where you saw in the videos, we have even the cracks on the road modeled, and the sensors will be able to pick this up. Awesome. So moving on from Ansys AVX, I want to talk about SPIOS. So SPIOS is kind of a subset and often used in conjunction with Ansys AV Accelerate. For companies that want to develop their own system, their own cameras, their own lens, etc., and Ansys SPIOS allows us to do that. It allows us to determine the performance of different filters as well as lens stacks to find the optimal sensor for your application. It allows you to determine the sensor coverage that your sensor would provide around the vehicle, as we can see right here, to demonstrate for you like how much of the environment is the car actually able to see, and put the car into scenarios like here where you're parking close to other vehicles where you don't need to damage other vehicles to do it. One of the best things about this software is it also allows you for a physics-based evaluation of human HMI interfaces, right? So this allows you to evaluate various lighting conditions, which include not only day but night operations, and determine whether how your system looks to a human in these conditions. One of the best things that we can provide for this is our sister set, Invest Windsor Essex, has a VR cave, and all the work that we do here is compatible with them, and we can work in conjunction with them to provide clients with access to the VR environment to not only simulate their results but actually experience it in the VR fashion. Okay. The next tool that we want to talk about is Ansys SDK. So SDK is a digital mission engineering tool that simulates complex missions in a 3D environment using virtual models. So Ansys SDK creates a digital twin of aerospace and ground vehicles that can include a drone, it can be a satellite, it can be a rover, you name it. It simulates the sensors. So this can be anything from radars, optical cameras, infrared cameras, thermal, etc. And you provided information about the terrain. So this would be what Alyssa was talking about with the 3D models. And you can also provide it atmospheric conditions. So this would be your temperature, humidity, winds aloft, etc., that are much more relevant for drones. Ansys SDK is normally used for much larger simulations. So here in the image, what I want to point out is this is a picture of our site where we have the zones, the different smart farms that we monitor, like outlined here as well. What we're doing here is launching a drone that we can see here in pink, and it plots its flight path as it surveys a field to report back on crop growth and etc. So what this software allows us to do is plan the flight in the 3D environment, determine the exact route that needs to be taken in order for us to be able to scan the 3D environment to a particular resolution that has been desired. This allows you to, so that the route that we have here, right, the trajectory of the drone, we provided the simulation parameters of the performance of the drone. We tell it that we want to scan farm A, and the software SDK is able to determine the optimal route. So this is where and how we're using SDK to illustrate as well as determine the optimal trajectories for these systems. The color overlay that you see in the background in green and red demonstrates signal strength from our ground station. This allows us to ensure that our ground station is able to communicate with the drone at all times and the mission can be conducted safely. SDK allows you to simulate not just the trajectory of drones or signal strength as a function of distance, but it lets you do a multitude of other things. We could also plot satellites and study their coverage over the entire Earth. Really, the missions are not limited to our Area X.O site, but they can be conducted anywhere globally. We can simulate telecommunications infrastructure of a mesh network of towers and demonstrate weak points where signal connectivity is at the weakest for a network. And we can simulate connected and autonomous vehicles that are dynamically moving to demonstrate how the connectivity of these systems change with time. I want to go through a little more general case description of digital mission engineering and what this entails, so we're not tied to just that specific use case of a drone surveying our field. So for typical digital mission engineering, we start with the engineer that's going to define the scenario. So this scenario can be anywhere in the world, right? We choose a place where we want something to happen. What we do then is, let's say we choose a system, right? This can be a drone, this could be an aircraft, this could be a ground-based robot, you name it. We choose our system and where it's going to conduct this operation or for this scenario in the globe, right? Now, this device, it can be able to do a multitude of things. It can be sent to identify and locate an aircraft. It could be sent to find a ship over the sea or a lost vehicle, off-road track. It could also be used to not identify quite a target, but to more scan an area. This would be more like the farm scenario that we presented slightly earlier. Now, we can also, throughout the mission, evaluate the connectivity of the drone to different satellites in the area for GPS connectivity to ensure that it's able to maintain accurate 3D position throughout its mission. And we can also simulate its connectivity to communication infrastructure to see how much data we can transfer throughout the mission. All of this defines a specific scenario, and it's set up by the engineer before we were able to hit start, right? So these are all the simulation inputs that the engineer provides to set up a scenario. And once we have the scenario, the SDK tool, it relays the output of the data. So similar to the example that we saw, this could be the drone. It'll output the trajectory the drone needs to take. It'll output the exact speed and position of the drone at each time. It'll output your connectivity throughout different communication infrastructure and the exact signal strength, the communication rate, you name it. All of these information is available through this SDK tool for designing missions. Okay. The next software I want to talk about is Ansys Electronics. So it's almost we could talk about it, smart infrastructure, smart cars, anything without communication infrastructure, right? And all of this is possible through electronics. And what Ansys Electronics desktop allows us to do is develop these systems. We're able to study the multi-physics simulation of how these systems work. So this includes the electrical performance, magnetic, thermal, mechanical, you name it. Different systems that we can test include antennas, motors, printed circuit boards, batteries, radar systems, and communication networks. What we have here as an illustration is the temperature distribution off of a printed circuit board, right? So we're able to determine the exact flow rate needed by the fans in order to keep the electronics within certain operating temperature range. We're also able to graphically demonstrate the electromagnetic waves coming off of an antenna, right, to ensure how it performs and whether it meets the design requirements. So different things that electromagnetics design can be used for is understanding these electromagnetic patterns, determining the radar cross sections of your obstacle. So this is particularly applicable in the autonomous vehicles where you want to determine what different objects look like to the radar. We're also able to determine antenna far field radiation, which helps you determine connectivity, and also work within the operating temperatures of our system. Our Ansys Electronics Desktop is a very complex package. It includes a lot of things. So I'm going to try to give a quick summary of different applications that we're able to cover. So we're able to determine the connectivity of different electronics to our infrastructure. We're able to simulate power systems, batteries, how they charge, discharge, and their management. We're able to simulate the electromagnetic interference as you're operating electronics to ensure that the power and signal integrity as it functions. We're able to simulate electric motors and how they're able to operate with their mechanical performance, and also the thermal properties of all these systems to ensure they're within the operating range. Right. So next up, I want to talk about some of the different aspects of simulation that have been used by a lot of these companies so far that work very well. So one of the main things that's been recurrently seen throughout the simulation services that we've provided is the ease of iterating designs and applying machine learning. We're able to modify the design and study its performance without the need of any physical prototypes. This not only saves time and costs, but it's also it's at an early design stage where you're able to make much more drastic changes easily. This allows you to determine what works before you start making something and you're committed to a design. We're also able to ensure system compatibility as we are able to compare our system with other systems that have been made, right? One of the other things, as Alyssa was referring to while she was presenting, is the training AI algorithms. The generation of data from all of these sensors can be used to train machine learning algorithms and sensor fusion algorithms before they're actually physically implemented. This allows you to have a much more refined algorithm right off the bat and get better success, and reduces the training time and actual physical testing that's going to be necessary before you publicly deploy your system. The other thing that simulation allows us to do is test in different weather environment conditions at your convenience. You no longer need to wait for a rainy day. You don't need to wait for a snowy day. That's possible anytime you want through our simulation capabilities. Right. One of the other things is to demonstrate the product performance. As you're developing product, it's very difficult to actually show what your system would look like without making it, right? So what simulation allows us to do is not only predict the performance, but visually provide you with the metrics such as these. So for DRobotics, this included their actual rover in the digital twin, where you're able to drive around and determine how the system performs. For electronics companies, this might be a depiction of your far field radiation patterns and a comparison to existing infrastructure that we have at our site. And the validity of our predictions comes from the fact that we're working with Ansys and their physics-based simulation tool that has been validated for ages. We also provide specialized engineering consultations to give you professional advice to determine what might work, what might not, and help you evaluate problems that you run into. We are able to provide an in-depth analysis of your system, where we use the Ansys simulation tools to determine what works and what doesn't, and how we can best help for your system. We're able to provide graphical results to show you exactly what's most relevant for your specific applications, and you have access to all of the models and data that have been generated in order to provide that have been provided to you. Our simulation capabilities have also been integrated with the physical testing that occurs at Area X.O. So it's a very good step to conduct the testing and see what you can expect and what you can get out of the physical site without having to make the commitment to physically come here with all your hardware. So this allows you to gauge whether it's something that's feasible and also something that is worthy of being demonstrated. The other thing I want to talk about is accessible support. What we're able to do for all these clients is for free of charge while we're working with the Ansys program is provide hardware as well as software to conduct all of these simulations. We have computers, high performance computers available on site or for remote access. So it's available for any eligible companies that want to use it, where you have secure file storage and can transfer whatever data is necessary to you. So you're able to keep all of the work that you do. And we're able to acquire Ansys software licenses that you need for your application. We'll work with you to determine exactly what's best. We also have the personal and technical help for your exact use case. You have access to the Area X.O engineering team, as well as Ansys for more complex questions that they might be more suited to answer. One of the things I want to quickly go over is a quick example of how much it would actually save you to collect data and run through a quick scenario. So let's say you wanted to train a machine learning algorithm for your autonomous vehicle. If you want to do the experimental setup using our autonomous vehicle, getting the machine learning algorithm as well as your sensors into the interfacing that with our hardware is going to take somewhere around 3 weeks. Booking for the smart city zone as well, depending on availability, might take up to 3 weeks. You're also going to require the help of our staff, 1 or 2 people, someone to actually operate the vehicle, and then more staff to aid with the test as necessary. And then collecting data, it's going to be however long you're able to run it, but you're limited to physical hours when the staff is here, as well as when the Lexus is ready to be operated and is available. Time to obtain data. Once you have the data, sure, it's within 2 hours you can transfer it. All in all, you're looking at up to 6 to 8 weeks in order to collect data that it's not running for most of the time, right? A lot of the time is being spent to set up as well as organize the logistics of this experiment. In simulation, we can integrate your sensors onto our Lexus vehicle in less than a week. Booking for the hardware computers, we're able to provide you time in less than a week's time. And the most you'll probably need is the support from one of the Area X.O simulation engineers to help you get set up. Like we did with 4D Robotics, I helped Alyssa set up the connection for their software to the Ansys. And once she was ready, she was able to work on her own remotely onto the software as needed. Testing can be, we say up to 3 hours continuously, but it's as far as you book it. So it's available and you're able to collect much more data than you can physically, right? Because you can leave it running overnight. There's no need for supervision once you have everything set up. And time to obtain the data, once you have it, you're able to download the data remotely at similar speeds. The total time you're looking at is less than 2 weeks, and much more of the actual time can be spent collecting the data and working on the data instead of dealing with the logistics and trying to get everything set up, right? And this is very helpful to provide you the mobility and the time to determine where you need to spend your resources, whether something's a good option before you commit too much to it, right? All in all, want to again advertise that our simulation community is available. You can join anyone can join our simulation community for free to learn more about the assets that we have at Area X.O and what you can do in our virtual environment. You'll have access to Ansys curated content, as well as access to Ansys as well as MathWorks software for eligible clients. You can also get signed up to stay informed about future information sessions. And yeah, a lot of our resources and content is only available if you sign up, and the website to sign up is visible right here. Yeah, and areaxo.com/simulation. And I think that's all I had for my presentation.
Perfect, Sammy. So thank you so much for providing that. So that was really a behind the scenes, excuse me, overview of the assets and capabilities available to companies such as the great company 4D Robotics. We're now going to enter into a Q&A period. I want everybody to, if you have questions, please throw them in the YouTube chat so that we'll be able to respond to them. And as we wait for some of those questions to come in, I just wanted to really put out a thank you to some of our government partners who have provided so much support and making sure that they can support this program and allowing us to bring it to all these great companies that we work with. So the City of Ottawa has done a great job with us, the provincial government through the OVIN network, and certainly FedDev Ontario at the federal level. So we want to thank them for all their support. Okay, well, we'll jump into some questions now. So Joe is asking, how does 3D mapping help to improve the safety and reliability of autonomous vehicles? Alyssa, Sammy, who wants to jump in?
I could probably answer. So one of the main things is that we can test the exact scenarios ahead of time before actually testing them on the track, where there might be people or there might be objects that could be dangerous. And we can test the exact scenario and then go to the site, run the same scenario, and it should do the exact same thing. So that's the main benefit there. It also allows us to test way more scenarios that could exist. Like anything that we can 3D model, pretty much, we can test it as a scenario. So we can test various people. We can test, especially people. Actually, is you can run a simulated car or a simulated vehicle at a simulated person, and if there's a bug in the software and the person gets hit, then it's not an issue. So you're able to test that really easily. Of course, there are mannequins as well, but especially with things like thermal cameras that need heat signatures, having the heat signatures in the Ansys simulation is really good. So it just makes those models more accurate, and we can just test way more and flesh out the software way more.
One of the things I want to add is what the 3D mapping allows you to do is it's what makes the simulation no longer a video game, but brings it to reality, right? It gives you the practical application aspect, and it brings the realism to what you're doing, right? So with our digital twin, when you run the simulations, we expect to get realistic results. What the simulation also allows us to do, like Alyssa was mentioning, is you can test the high risk scenarios, right? You don't want to see what it's going to look like for a car to crash, right? But in simulation, you can do exactly that without the price of having a totaled car at the end of the day. So you can get sensor data of what it looks like milliseconds before a crash from your LiDAR, from your radar, right? Do sensors get obscured based on how the vehicle crumbles, right? All these things that it's very difficult to, they're very expensive to do physically, you can do now. Yeah.
Great. Thanks, guys. Yeah, you both hit on that very well in your presentations in terms of that data and the predictability. So thanks. We'll take that next question. So Salma asks, how does the software react to different weather patterns, including fog, snow, and heavy rain? Both of you guys alluded to this a little bit, but specific examples would be great.
Yeah, so for the Ansys software, if we're talking about AVX, it's very good at handling fog. I didn't have any images in my presentation, but you kind of saw in the beginning video where you're able to do day and night, right? So there's different lighting conditions throughout that you can simulate. With the fog, you can exactly see like the depth of vision, right? And based on the exact lens and the wavelength that you're operating at, the software, you'll have the loss of different wavelengths at the different, depending on the humidity as well. For the drone operation, where a lot of these weather conditions, including humidity, winds, etc., are much more relevant, SDK does a great job where you can download live data from the internet at different altitudes and simulate to the exact weather conditions. This will evaluate your engine's performance to exactly that altitude, the density of the environment, the exact humidity levels, etc. So all of this is actually captured by our simulation. Yes.
Got it. Anything to add there, Alyssa?
I'm assuming that they were asking about the software response from Ansys, so I think Sammy's probably got that one.
Yeah.
Perfect. That's great. How about our next question? What are the challenges and limitations of using 3D mapping and simulation in autonomous vehicle software development? So, everyone's talked about the possibilities here and the great opportunities, but any challenges you're aware of already?
It's getting a 3D model good enough to use, right? So you kind of saw that with the work that 4DRobotics was doing in the beginning. It takes a lot of time, it takes a lot of effort to have a machine-generated world that is actually comparable to reality. And we've tried to alleviate a lot of these hindrances at Area X.O by trying to do the work for you, right? So
as well, sorry, what was the exact wording of the question again?
Yeah, it was the challenges and limitations of using the 3D mapping.
So one of the biggest things as well is actually making the simulation so similar to the map being accurate, but you also need to make the actual simulation accurate. So getting accurate movement, getting accurate sensors, just setting all those up is a lot of time, and Area X.O and Sammy have been very helpful with that. Like Sammy made some scripts and things to make like LiDAR scanning files and all that. And yeah, so that kind of stuff is like, it takes time to get it right, because if you don't get it right, then you can get like garbage in, garbage out. Like if you don't provide the correct properties and everything, then it will not actually give you good data. So just making sure that that's correct and comparing it to real life and tweaking things and stuff like that and getting it as accurate as possible. That's probably the
kind of on that. I like to say, like, if simulation, you have to like know the exact settings that we're working with. That's where the access to our engineers is very helpful, right? Because we've been trained on this software. We've been working on it for a while. We know what's going on, right? So it's free of charge that we're here to help you with. So you don't need to know how to use it, right? You come up with the vision, and we'll help you figure it out.
Nice. What I'm interested in this mostly. Hossein, Sammy, and Alyssa, what was your biggest surprise in the case study specifically around the 4DRobotics project?
Biggest surprise probably would just be the amount of properties that are that exist for different sensors that need to you need to know what those properties are in order to get reliable data. So just the biggest surprise is like, well, for one, looking at all those properties and realizing you don't have all those properties. So you need to figure them out from what you do have. And because a lot of the stuff for the properties in the Ansys sensors as well are not properties that companies will post in their data sheets usually, because they're just not relevant to actually getting the data. But in order to model the sensor, they're pretty relevant. For instance, like the LiDAR scanning sequence file or the pulse energy and things like that. So I'd say that was probably the biggest surprise.
Yeah, and it's also been as we were advertising with AVX, we're able to connect with the simulation that the company already has, right? So there was a significant undertaking, and we were able to work with the actual Ansys team, and they were able to provide us with the script, right? So we've had to lean on the Ansys team for support sometimes, and they're here now.
Great. All right. Well, thank you both for answering some of those questions, and I'm just going to bring us home here with a final conclusion. But I wanted to thank Alyssa Turner and Sammy for taking all of your time and putting these presentations together. It was very useful, and it's so nice to see a specific use case in terms of the overall assets and capabilities that are available through simulation. So thank you for that. I also wanted to mention that we will be following up today's webinar with a recording of the session as well as a survey for you to respond to. If you're not already a member, as mentioned by Alyssa and Sammy, we invite you to register for free to become part of our simulation community. And it's easy to register on the Area X.O website. If you have any questions that have not been answered today, please send those to simulation@areax.o.com. And we want everyone to have a great day and a happy holidays. And thanks for joining us today.